Okay, so let's start. I hope everybody sees the screen. If you don't see the screen, then just put the note in the chat message. It's not related to the people who are joining through the phone. I saw one person doing this. I'm sorry, but this is going to be done in the Jupyter notebook that you see right now on your screen. I'm not going to go into very much details about what the Jupyter notebook is or how to use Python and so on and so forth. So I assume that most of you know this kind of things. I'm just going to give you some very general overview of what can be done. And about the details, you unfortunately will have to maybe find out by yourself or just asking the question afterwards. And first thing that I would like to do is to actually tell you a little bit about the unstructured meshes. Most of the people, when you say that your model is on unstructured mesh, are quite, I would not say afraid, but quite hesitant, let's say. But in principle, the unstructured meshes is not that difficult. In principle, for working with pyfesom or to work with pyfesom2 output with pyfesom2, you don't have to know too much about unstructured meshes. Only if you want to do something a little bit more complicated than just usual diagnostics. But to look at your fields and so on and so forth, you don't have to know almost nothing about. You have to know almost nothing about them. And just a brief explanation of what it is. We can think about our mesh as just collection of points, and these points is these blue dots. So we call them vertices. So their official name is vertices, but I will most of the time will call them nodes, and this is for historical reasons. We just instead of vertices call them nodes. And these nodes or vertices, they're connected through by connected to form triangles. And this is the basics of it, right? Then similarly to the structured meshes, you have to place your variables somewhere on these triangles or on this mesh. And you have several main options similarly to the structured meshes as well. You can put your variables onto the nodes or vertices. You can put these variables onto the centers of the triangles, or you can put your variables onto the edges of the triangles. In pyfesom2, we only use nodes and centers of the triangles, and the nodes and the variables on the nodes are actually most interesting one for most of the people is temperature, salinity, all the scalar variables, most of the scalar variables actually located at the nodes, and the vector variables like u and v components of velocities, they are located at the centers of the triangle. And of course, if you want to do some summations or aggregations, or you have to know the weights, that basically the volumes or the areas that that are associated with this point, for example, right? And for this point, it's pretty simple. It's a triangle, right? So for u and v is just the area of the triangle that would be your weight in the weighted mean, for example. For nodes is a little bit more complicated, so the volume will look like this, but you don't have to think too much about it, because this field that associate the area to each of the node, right? So basically your weights are provided for you as well. So that's not a problem. And again, if you just think about this meshes as just collection of points, that makes your life much easier. So most of the time you don't have to even know about the relation that these points have to each other. They have that's a point with a lot of weights. So for many applications, it's fine. If you want to know more about how the mesh is constructed and how the geometry looks like, we have relatively good documentation. I will just make the things a little bit larger. We have pyfesom2 documentations, and there is this geometry and meshes sections of this documentation where you can learn a little bit more about what's going on with the meshes in pyfesom. Okay, now let's move to pyfesom itself. Paul, okay, Paul, you have a question?
Quick question about the documentation. Does that relate to pyfesom or to FESOM itself, the Fortran program?
No, this is related to pyfesom2 itself. So this documentation is only describes the basics that well, it's a little bit more complicated that the information that you need to work with pyfesom, I'd say. So yeah, so it's
okay.
It's basically FESOM2 read the docs, so it's FESOM2 documentation. Yes.
Okay.
Okay. So pyfesom2 is located on GitHub. It's open source development, so anyone can contribute to it. And we also have some documentation about pyfesom2, although it's not like super extensive one. But this is your GitHub page. And here, if you move down, if you're not really familiar with GitHub, usually on the GitHub project, you scroll down the code, usually you have some more information about the project. And in this case, here is also installation instructions. I'm not going to go into too much details about it, but you just have to notice that in order to install pyfesom2, you have to use Conda. That's the only supported, let's say, option available by now. And if you don't know what the Conda is, there are two links to that will hopefully explain you a little bit more about what Conda is for Linux and Mac and Windows. But again, for Windows, I don't know anything about Windows installations of Python. And I'm not really sure if pyfesom2 is going to work. There is no reason why it shouldn't work, but I never tested it, so there is no guarantee. And then the installation, well, procedure is relatively easy. You just clone the repository. And then the next step, you create the additional environment. At this step is, well, like, I mean, it can be optional, let's say, but if you somebody who is relatively new to Python or Conda environments, is better to do this. And maybe I have to update from py36 to py37. The py37 file actually also exists, so probably it's time already to move a little bit further in the Python versions. But what this thing will do, it will create a separate environment that will have only pyfesom installed there, and not only pyfesom, but also, guys, do you have a question, or Dima Vera, do you have a question, or you just don't switch off your camera? Okay, they don't have a question. So the
Not yet.
Not yet. Good. So the environment that will be created will contain everything that you need for pyfesom installation, and nothing less, nothing more, right? So you can actually activate this environment, and later, if you don't need this environment or you don't need pyfesom, it's very easy to just delete it. The next step, you just go to the pyfesom directory and just say pip install -e dot. Right? This way of installation will allow you to, yeah, you have a question? You have to turn on your microphone, Frank. Yeah, shoot, no? You turned it off again. Now you.
Okay. Hi, Nikolai. Is Miniconda working as well, or do we have to install Conda?
Well, Miniconda, part of the Miniconda is Conda, right? So Conda is basically comes with Miniconda or Anaconda. So Conda is a package manager, right? And Miniconda is just the minimum amount of like Python libraries, Python itself and Python libraries, but Conda is the integral part of it, of course. So you will get Conda with anything that has Miniconda or Anaconda in the name.
Okay, thanks.
Sure. Can you also turn off your camera, please? Okay, so with this kind of installation is also like relatively useful even maybe for the novices, because if you start to change something in the library, this changes will be actually reflected in when you do the import, let's say, right? So -e means editable, so you can edit your library and then reload it, and then your changes will be actually applied, which is not the case if you install it with a normal sort of installation thing. Later on, I hope we will do it in a little bit more convenient way with just conda pip install pyfesom2, or not conda, but pip install pyfesom2 and conda install pyfesom2. But right now, it's the way it is, right? And it's actually worked more or less fine, at least for me. So installation instruction is, well, again, it's just directly into installation instruction. Also in this file, I sent it a little bit earlier today, and for those of you who might had a chance to actually download the data, you can maybe execute this examples together with myself. But if you want to do something afterwards, you can download this data from this link, and you have to download this lcore.tar and lcoremesh.tar files from this folder, and you will be able to execute examples. If you don't want to download this 15 gigabytes of data, alternative would be to use some data in mesh that is available in pyfesom itself, because we need it for testing. So, and there is this folder test/data/pygrid. It's a very small mesh, and test/data/pydata. It's the data that was generated with this mesh. So, if you change the paths to this directories, you might be able to repeatedly some of the things that we are doing here. Okay, so pyfesom was designed in a way that can be useful for people of different levels of Python experience, and the highest level is the level when a person doesn't want to have any Python experience at all, right? When you just want to maybe have a look at the fields, check very simple stuff, don't do any crazy computations on the original mesh, for example, and you don't really care about like crazy ways of visualizing the things. And for this, we have two command line utilities called PFinterp and PFplots. Maybe PFinterp is not the best name for it, but yeah, it's the way it is. PFinterp allows you to actually interpolate pyfesom, or not pyfesom, but fesom data onto regular grid. And then you can look at it or analyze it with a tool of your choice. Usually the tool of my choice in this case is NCView. You just create a netcdf file out of the, with regular grid out of the netcdf files of fesom2, and just visualize them with whatever you want. And usually this whatever you want is an NCView. So the minimum arguments that you have to provide is path to the mesh and path to the data folder and the name of your variable. So let's have a look how this, if it's gonna work for this minimum example. And as you see, it doesn't work. And the reason for this is that you have to always remember that you have to do conda activate pyfesom2. So you always have to activate your environment when you're trying to use pyfesom. And since when you activate the environment, then this PFinterp function is actually available for you. And you can get the help by just typing help to understand what all of these instructions means. There's also documentation, but let's try to repeat the thing that we tried to do a minute ago. So PFinterp, path to the mesh, path to the data, the variable. What will happen is, well, there is some information for you, and you get the new file which called out.nc. So this is default name for the output files here. ncview out.nc. You have the data that you can look at in ncview. This is PFESOM data interpolated to a 1-degree grid. This is again the default setting, and you can immediately, well, I mean, this is ncview, right? So a lot of people use it, and you can do whatever you want and whatever you can with ncview with this data. Okay, let's look at a little bit more complicated example. This one. Well, what will happen now? Something happened. Again, the name of the file is the same, so we can just open it. But you see right now, you just selected some region, and again, interpolated the data from PFESOM to this region. It's especially useful when you're working with some high-resolution meshes and you're interested in some very small or relatively small area. How was it done? So what are the options that we use to create this this smaller box, not the global one? Yeah, Paul, you have a question?
So I assume this does some sort of interpolation in the background to the linear boxes. Are those weights saved for reuse, or are they made again?
Yeah, that's the trick. Yeah. So the idea again behind pyfesom is to make things as fast as possible, because it's aimed at for the quick looks and so on. And if you do this kind of interpolation, especially to some standard regions, you have well, you just create weights over and over again, right? So the idea is, of course, to save these weights. And the weights for each region that you select, and each region and each resolution is actually saved by default is in the mesh folder. So my mesh folders looks very messy right now, but that allows you to reuse this interpolated weights, and the next time you use the same box and the same resolution, you don't have to interpolate. You just the weights will be just reused.
What if I can't write in that folder? So often we share the meshes between different people.
Well, it's you have to, like, right now the idea is that you just have to copy the folder somewhere. That way you can write. But in principle, in the interpolation routine, you can specify the folder. So it's relatively easy. If it's needed, we can add the option to actually save it somewhere else, or look for it somewhere else. And that's already, like, functionality is already there, but it's not implemented in PF but if it's needed, well, it's 2 minutes to implement it.
Okay, thank you.
Yeah. Okay, so just to explain these two options, so -b is actually selecting the region, so from -19 to 0, from 20 latitude to 60 north, and -r is actually your resolution. This is what I just talked with Paul about, right? And this is the information that will be your weights will be identified with as well. So the resolution means that from you want to have 360 points in this direction, in X direction, and 160 points in the latitudinal direction. And this is how your mesh, the output is created. Okay, let's look at some more complicated example. It might take some time to actually execute this one. There is some questions in the chat already. Yeah, okay, something finished. I will just answer Christian's and Paul's question from the chat after I finish this section. Okay, so something happened. We now have a different file called output.nc. let's try to look at it with NC view, and this is terrible, right? So this is not really what you want to see. You have these white spots in the places where you have low resolution, if you know the Core 2 mesh. The reason is that in order to do interpolation, we have to use something that's called radius of influence, and that's mean that we, like most of the time, we use nearest neighbor or inverse weighted distance interpolation. And for this, you want to limit the radius where the nearest neighbors actually looked for. So, for example, if you have, and you have points because you have a regular grid, right? So you have points somewhere here. If you don't limit the radius of influence, you will end up getting the points from the oceans at the Eurasian and the Eurasian continent. So that's why you basically it's better to not better, but you have to actually limit your search for nearest neighbor. But it's a bit complicated again for PFplots because you have different resolutions in the meshes. So the rule of thumb, if you don't really care, if you're not really peculiar, you just have to set this radius of influence to the highest value of to the lowest resolution that you have. And right now we actually use the option that is 40 kilometers right here. So this minus E is this radius of influence. Unfortunately, the minus R was already taken, so I had to use the minus E. And instead of 40, we just put here 160. So this is in meters, so 160 kilometers. Let's see what happens here. Okay, you see everything is fine now, right? So you have, well, nice, more or less nice field. What else do we have right now? We have 3 time steps. So it's year 1950, 1951, and 1952. The output that I'm using right now is has yearly data for 3D temperature, so that's why it's only three time steps and 3 depth levels, right? How did we specify this in the PF interp? So here is our years. Years are defined by -y option, and you can specify them as just a list as a range, and this is shown here. And the last year here will be included in the computation. So I decided not to follow the Python route and just include the last year as well, because that's what most people expect. Depths are defined by this -d option. You can just specify depths like whatever depth you have in mind, but the depths that will be returned, you can see them here. They are actually the depth of the model mesh. So the closest depth to your desired depth will be found and returned, right? So you cannot expect that. There is no interpolation happening here. So it's just returning the mission.
And what about the coastline? Do you define usually the mask for the land area, or you define it only by the radius?
No, the mask for the surface. So basically, the mask is defined by the coastline, and this is nicely. That makes your first level look okay, right? But for the deeper levels, unfortunately, we don't have the mask for the deeper levels. It doesn't make too much sense for me to go into this this trouble, I would say, and that's why the mask. If you plot something in the deeper layers, that's where you have to be careful with this radius of influence, because there the sort of mask will be defined by the radius of influence. But then the surface, I try to make it look nice at least. So that's just masked by the natural Earth coastline. I think it's 50 meter with 50 meter resolution. Okay.
So
yeah. Is there any?
I have questions about this this lengthy mask. But if we want to interpolate the data for the paleo coastline or paleo topography, then this method also works.
No, it's not. Well, I mean, you will. Yeah, you will have troubles in this case. Well, the idea would be you can just make an issue on the pyfesom2 in the pyfesom2 repository, and just to remind me that maybe it's a good idea to turn this option off from time to time, because then for you it's gonna screw your visualization, of course, because it will mask according to the current coastlines. That's true. So it's probably then a good idea. Most of the people who doesn't work with paleo data will not want it, but for paleo people, if you want it, I can include it, no problem. And another thing related to this is, please don't, if you have a question or suggestion, please don't send me email. Just do open an issue on GitHub, because if we have a conversation on email, it just lost forever after a couple of weeks. And if we have this conversation on GitHub, then other people can find it. So please don't send emails to me. Please make an issue on GitHub. That would be much easier for everyone. Okay, let's move on. This is depth. That was defined. Okay, we discuss it. Resolution. So you see that it's a quarter-degree resolution right now for the interpolation, for the target interpolation. That's why it took a little bit longer. And this interp option actually allows you to select from different interpolation functions. I also implemented here the couple of functions from SciPy, but first of all, they work much slower, and second of all, they are not always they sometimes produce very strange results. So there's linear interpolation available. You can try it if you wish, but it will be slower, and you might not be happy with the results, at least right now. And for inverse distance interpolation, you have to specify how many neighboring points you want to include in the inverse distance interpolation. Of course, they will be limited by this radius, but well, I mean, if you increase it, sometimes the results looks a little bit smoother. And the -O option here is just to name the output. So you see that you can basically use it in your shell scripts if you wish, just to batch process some of the data if you would like to process them with bash scripts. Okay, I think there is this another two examples of PFinterp, and then we move on. Okay, so here I showed that also our vector data can be interpolated. So in this case, I interpolate the U. What is CU? That's how it looks like. Interpolation of vector data is, well, let's put it this way. You can look at the interpolated vector data. You can maybe even create movies with them, and everything will be fine, but please don't use it for any calculations. Never, ever. If you want to compute transport, never use interpolated data for your computations. You have to work with a regional mesh. And Dima Sidarenko did some Jupyter notebook that is available also in pyfesom right now, of how to do it properly, like really properly, and at some point we will implement it also in maybe a little bit more optimized and more user-friendly interface. So there is a way to do it properly, and don't do it with interpolated data. But if you want to just look at the things, just look how your currency evolved and so on and so forth, that's perfectly fine. Another thing that you have to keep in mind that our data are on the vector data are on centers of triangles. In order to interpolate them, I first interpolate from centers of triangles to nodes, and then from nodes interpolate to regular grid. So you see, once again, I cannot stress this enough. Don't use it for anything that is kind of scientifically relevant. It's just for having a look at it. And the last thing, I just wanted to show that it's well, it's pretty fast. Actually, it's related to the question that Paul has. Because the weights are saved, you always reuse them, and even for the 1 kilometer mesh in the Arctic or our 20 million mesh with Rossby radius is actually pretty fast because it's just reusing the weights. And right now I just computed interpolated the CIS data from I think how many years? Well, okay, 3 years, but it's every year has some monthly data, and you see that for each month it took less than well, it's not even a second. It was relatively quick. And here you can look at your CIs data. Okay, so that was PF interp, and let's have a look at the chats. We have some questions here. From Christian, is there any experience with using pyfesom2 directly at GKRZ? It should work out of the box if one just makes their own conda installation. Exactly. So if you're using your own conda installation, then it will work out of the box. When the pyfesom2 is more mature, we will ask to GKRZ to install it as a standard. Paul, you can use GKRZ. Okay, so Paul answer to Christian, I think. Paul, does this support CDO similar syntax with / for a range of levels, or do you need to give a comma separated list? For depth is only comma separated list. You can use this. It's not a / in my case, but it's this column that you can use for years. Unfortunately, for depth, you have to provide the list, and the reason for this is that it would be while it returns you the well, I mean, I think you can implement the range as well, but I just didn't do it. Frank, what about interpolation on, for instance, polar stereographic grids? There is nothing that prevents me to do this, except for right now, like what you have to do, you have to provide some kind of a standard grid that you have to interpolate to. How internally it's organized, you just provide the bunch of latitudes and longitudes, right? So it doesn't matter what kind of grid it is. It's just easier for now to generate this grid by just defining the ranges in latitude and longitude. But in pyfesom, like in my daily work, for example, for our 1 kilometer resolution simulations, what I do is to interpolate to MITGCM regular grid because it's easier to plot it than afterwards. And this is also can be done. And that's also something that I'm thinking about, but for this I have to like select some of the grids, some of the standard grids. So you will not be able to actually kind of select whatever you want, but you have to say, okay, interpolate to the North Pole with resolution of, I don't know, 25 kilometer and 4 kilometers. So for example, these two grids I think will be enough. But that's something that I'm gonna implement at some point, yes. Okay, so the other command line utility is called PFplots. I'm not gonna actually spend a lot of time on it. I was first very inspired when I started to create it, but the thing is that it's most of the time just easier to use ANSI view, because what PFplot does, it just allows you to look at the data, but it's again just do interpolation, and this interpolated data uploaded. Maybe the more useful thing will be something that will allow you to look at the data uploaded on original grid with some interactive capability. Again, this showing up this plot is also not super fast, so something that you can use, but well, really, maybe it doesn't have too much love from me in the last couple of months. One advantage maybe here is that you can relatively easily zoom into the regions that you're interested in, and you can then go with this interactive thing through your model domain to see maybe if there is some strange things happening. But yeah, again, maybe it's easier for you to use one of the tools that you get used to already. Okay, there is another question. If you use CDO, / just makes a sequence of integers with step size 1. Okay, no need to verify whether level code actually exists. Yeah, well, I think people start to chat between themselves already. So, okay. Or if it's a question, then I didn't really get it. Okay, if there is no, now it's a good chance to actually ask a question about this command line utilities, if you have one. Doesn't seem to be the case. Or, oh, there is a chat message. Okay. So then let's move to the pyfesom kind of lower level of the pyfesom2 to the basic functionality, and that aims to at the people who actually would like to use pyfesom or work with the FESM data in the Python environment on Jupyter Notebook in particular. So what you first do, you of course import pyfesom, and the usual thing is to make it shorter, so not to type pyfesom all the time, and just import pyfesom as PF. Then you have to load the mesh. The mesh is, well, just provide the path to the mesh, and sometimes you have to provide them, not sometimes, but well, sometimes, because by default is 0, 0, 0, but we have this problem, not the problem, but peculiarity of FESM right now, that you can provide rotated meshes and unrotated meshes, and for unrotated meshes, which are majority right now, you have to put this to 0, 0, 0, but our standard mesh, which is a core mesh, is still the rotated one, so that's why you have to provide this angles of rotation. And the reason for this is we try to avoid the singularity of the North Pole. That's why internally the model mesh is actually rotated in a way that the North Pole is located over the Greenland. So the what you get when you get what you get back from this load mesh function is the mesh object, and this mesh object contains a lot of useful information, but the most important ones are these three guys: this x2, y2, and lm. So x2 is positions. It is longitudinal positions of your points or your nodes or your vertices, whatever we call them. And the same is for y2, but it's latitudinal positions, right? So this is your x and this is your y. And mesh lm is actually how these points form the elements, right? So to each of the points has its number, because this is point number 0, this is point 1, 2, and so on and so forth. And by providing these numbers, you can actually form the triangles. That means that the first triangle is formed from the point number 1763, 9600, 635, and so on and so forth, right? The simplest way, for example, to get all the latitudes that your, all the longitudes that your triangles have is to do something like this. So you can see that for the first your first triangle will have these longitudes, and you can do the same for latitudes as well. And you see that they're pretty close to each other, but the indices, for whatever reason, is pretty far away. So that's the mesh is not really nicely sorted, I would say. Okay, that was the mesh, and this mesh object is actually something that you use almost all the time. We don't have, for PFESOM data, doesn't have as an output the mesh associated with them, because it's usually, especially for large meshes, is pretty heavy. So we just store it as a separate object. It might change in the future for some applications, but right now the mesh is just something that is quite separate from. Yeah, there is a question.
Does the mesh also contain the vector points?
No, there is no centers of triangles in the mesh. Although there is, I think I added a function to actually compute the centers of triangles relatively easily somewhere, but we almost never use them. That's why we don't have them. It's relatively easy to compute. The only problem, because you can just make average of the of these points, and you get your you get the coordinate of your central point, but the problems start to appear on the edges. So if you work inside some area, it's not a problem. You just make an average of latitudes, and and longitudes, and will be your central point of your triangle. But yeah, there is a function. I don't remember where it is exactly right now, but there is a function I hope I added in pyfesom2 that actually computes them. So that avoid this problem on the across the international date line. So this is also possible.
Okay.
Yeah. Okay, getting the data. The thing about getting the data is the following. We distribute PFESOM2 data distributed in usual netcdf files, right? So you can open them with whatever netcdf standard tools you want, like netcdf4 and so on, or even I think SciPy. Like for many applications, you want to have the data in something that is called X-array, that allows you to work with a lot of data out of the core computations. That means that you can do computations even if your data are larger than your operation memory, for example. Or if you have like terabytes of data, you can actually do your, for example, aggregations in parallel. For most of the users, though, it's maybe not that necessary. That's why, and sometimes even for large data, well, it's better to use just pure NumPy arrays. That's why I just try to write a thin wrapper around the X-array and NumPy arrays. That, I mean, you can choose what you want to get at the end from PFESOM. I hope it makes sense to people. But maybe it will be a bit more clear when we go deeper. And another thing is that for all the functions with pyfesom2, I also try to make sure that they both work with X-array arrays or X-array data and pure NumPy data, because like experience show that the X-arrays is not always the best solution. Sometimes you just want to work with pure NumPy. That's why, yeah, this kind of choices were made. Okay, enough talking about this. Let's use this getData function. To use it, you have to provide a path to the output results, the name of the variable, the year or years. We'll see how to specify more years later on, and the mesh. And what you get in return is the data, which is just a NumPy array. So by default, you're working with just NumPy array. You have as the result just a NumPy array, and that's the shape of your NumPy array. Hope you you're familiar at least a little bit with the way the PFSOM2 data are organized. If you don't, just a quick thing is that our data are organized in kind of one-dimensional arrays one-dimensional array per layer, right? So each layer is just one-dimensional arrays, not two-dimensional array as in regular grid meshes, but it's just one-dimensional array. So it's just basically a bunch of points, and this bunch of points correspond to the size of your 2D nodes, right? So this number and this number should coincide, otherwise you're in trouble. And then there are 47 levels. Yeah, Paul, you have a comment?
Yes, so if you go back up a little bit on your notebook to reload the data, up 2 cells or so. This part, yeah. So there's no actual .cdf file in that path, right? So there's some assumption about how your folders are laid out.
Yeah.
That is made.
Yeah, it's assumption. The assumption is that you have a standard PFSOM output. I think you can still specify this, yeah, PFSOM run ID, because sometimes you can have it have a different PFSOM run ID, but usually our data are specified as temp dot I think year dot PFSOM dot nc or something like that. And there is an assumption that you follow this this thing, yeah. So there is, if you rename your files, then you're in trouble. One thing that is also possible, you still can provide directly the netcdf file itself. It also will then work, but well, for example, if you want to look at the restart files, then you can just provide the path to the restart file, and you will have more or less the same functionality, but then it will just work with one file. That's it. That's it. So you will not be able to select like five restart files, for example.
Okay.
Okay. Yeah. So the shape of the data is like this. So you have so basically this means that you have a 3D field, right? Because this this one-dimensional array actually represents all the cloud of points that you have for one level. Okay, let's try another command, which doesn't work for some, okay, for this reason. Here we have years from 1950 to 1952, yeah, sort of. But what you get back is also a three-dimensional array in the PFSOM sort of understanding, right? So it's just basically one data point with one time step with three-dimensional data in it. The reason is that by default, the things that you like most of the time you want some aggregation out of your function, and this some aggregation is actually a mean. So most of the time you just select this, I don't know, 10 years and make a mean out of them. That's why by default the pyfesom just assumes that you want mean over these years. Another thing to yeah, and then if you just the way of aggregation is controlled by this function that's called how. So here it is, and by default it's mean, and then you have options of selecting, where is it? This how thingy, yeah. You have options selecting minimum, maximum, median, again minimum, sum, standard deviation, variance. So you can return these things, and if it's none or something else, for example, like here, then you will get your original data back. So there will be no aggregation applied to your data. It will just return you the things that you sort of ask for. Please note that here we have a specify 1950, 1952, and you have only 2 years in return. And the reason here is that it's different from the PF interp. Is here we in the Python world, so the last number here is not included in the final in this range. That's why you only account here for 1950, 1951. So you have to remember about that. If you kind of feel uncomfortable with this Python style, you can just say 1950, 1951, 1952, just to be sure, and you will get your 3 years in return. So basically, it somehow should be a list of the values that you of the years that you want to use. Okay, what else? And the last thing that I would like to show is that you can return the X array, and for this you have to say compute false and how none, right? So please don't do any aggregation on my data and don't do any computation, because internally when you say make a mean out of my data, it actually do computation with X arrays. And let's execute it. Let's have a look. Yeah, now you have an X array as the data. You have 2 time steps. You have this nice new visual representation of X arrays. Yeah, this is just steps, and your data are not yet actually even loaded, right? So then you can do some operations, but this is like, I mean, I'm not going to talk about X arrays right now, because I mean, then you probably have to learn about them by yourself somehow. One thing to note for people who know about X arrays is that you can provide chunks as well immediately into this get data. So as a return, you will have a chunked X array that is ready for your parallel computations and so on. And then you can apply for this to this data the usual X array kind of pipelines, where in this case for you just make a mean over time and compute it. And then you, like, since we, yeah, so, and the data for this final computation will be now actually loaded instead of lazy computations that we actually have here. So nothing is computed here and something is computed here because the computer is here. But again, this is very specific to X arrays. If you don't feel comfortable with X arrays, and if you work with small data, just don't think about them. Just use this get data with that will return you the n-dimensional NumPy arrays. There is a question in the chat. It is possible to get lm no none like pyfesom1. Yes, it is possible. It's part of the mesh. So you have it here. Mesh lm. It's not lm, but no cyclic lm. So this is how you do it. You can have a look at what there are many other, not so much, but some other things in the mesh that you can find useful. Okay, so the next thing is plotting. This may be the most important for most of the people. You want to look at the data as quickly as possible and as simply as possible. And the simplest way to look at the data is just using the plot function that accepts mesh as an argument and one-dimensional array. All right, and in this case, we don't have to. We have to actually we don't have to use the X arrays. We have to use just NumPy one-dimensional array, and this is how it should look like, right? So just a collection of numbers of the shape of your nodes, and this then will work. And what it will return to you is just a global 2D plot of the values. Again, everything that you will see here is interpolated. So this is not something that is plotted on original mesh, because for larger meshes it becomes very time-consuming, and it goes not in line with the idea of pyfesom for being as quick as possible, for at least for things that you can make fast, and that doesn't matter that much if you use the original mesh or not original mesh. And if you thinking about looking at the data, like an overview of the data, this is the interpolation. The interpolated data is good enough. Okay, and now we will go through some options of the plotting. You can, let's execute it first. You can say that I would like to have a North Pole map projection. So there are several map projections available already. You have to, like, for North Pole or stereographic, unfortunately, you have to specify this box, so it's not gonna work straight away. But then you will see something like this. This ugliness, this too thick color bar, something that I'm working on right now. Is something that like appear in the new matplotlib. I'm not really know how to fix it. If Python people know and can advise me how to fix it, I would appreciate it. But in principle, I mean, there is a fix that I will show a little bit later that actually sometimes helps. But again, this is not aimed at the publication, right? You can show these things for people in your group, let's say, and so on and so forth, and look for yourself. But if you want to do publications, just look at the pyfesom code, how the plotting is organized and modified, because then everybody does the plotting, like the final plotting, their own way. Okay, a little bit more options here. For the next example, I just load the different data set, not the different data set, but just different range of the years. So it's 1952, 1953, make a mean out of it. I just put it explicitly, but like it's a default thing anyway. And what you can do now is actually compare one field to another. And in order to do this, you just provide, instead of just one data, one-dimensional array, you have to provide two one-dimensional arrays, and these two one-dimensional arrays have to be in the list. So it's just a list of one-dimensional arrays. Why I have point values here is just only because this one is X array, and that's why I have to put these values here, and this one is just NumPy array, so the values are automatically kind of extracted from it. And what you get in return is these two plots that are next to each other. Unfortunately, you cannot really plot different properties. You cannot plot temperature and salinity. That would make things too complicated for me, and the function that is already pretty monstrous and have to be refactored would become even harder to handle. So that's why you just have to work with only kind of one property, but you can put as many panels as you like, and the things about the panels are controlled by these row columns, and you just have to provide how many rows and how many columns you have, so you can actually change it. And then you have to change the figure size as well. Let's see what will happen. Yeah, you have it in this layout. Again, something that has to be fixed. Something that bothers me now. The way to fix it right now is to actually apply the safety. So this thing is completely the same as the previous one, but just apply this PLT safefig to some test document, and this is how I want this thing to look like, right? So for whatever reason, this thing fixes the ugliness that you see above, but yeah, again, something to work on. But the idea, I think, you get that you can actually plot several panels with one go. And the last example, I think, here is that you can, well, subtract one from another, so you will see the difference here. You can apply different CMAP. Let's just execute it first. Different levels. You can provide the units and titles, and it will be plot here. So some basic tuning of the plot you can do, so that it's not super, like, not very very naked, let's say. But well, it's not much, right? And again, for final plots, please use maybe look at the internals of pyfesom, look how it is done. It's very simple. Like, I mean, all the plotting stuff is like super simple. It's 5 lines of code usually. So it's nothing complicated. Okay, there is a question in the chat. Can you plot more than two panels next to each other? Yeah, you can plot as many panels as you wish. So there is no limit on it. It's just this. Yeah, you just have to put 5, 7, whatever. So the array of panels can be any. I don't set any limit. You can push it to the limit. I don't know. For the color bar thickness, maybe adjust C bar aspect. Defaults 20. Yeah, okay, I will try. Yeah, have to work on it. Before was fine. Now it's just, yeah, strange. Okay. Do you have any questions to the plotting? Doesn't seem to be the case. Then let's move. Okay, we have, it's already 1 hour here. So I'm just remind you that we have to finish in, I think, about 10 minutes before 4, because the next group is gonna occupy this room. So I have to be maybe a little bit faster, but although there is not much actually that I have prepared anyway. So another thing that you can look at is transects. And transects are just a collection of points, right? Here we allow the data because we want to look at the temperature and the 3D temperature once again. And you have to provide to the plot transect function something that is called lon_lat. It's just longitudes and latitudes of your points. It can be any points. You can generate them by yourself. There is a helper function that actually can generate the transect for you if you specify the start point and the end point and the number of points in between. So let's use this and let's have a look at this lon_lat. So we have a transect along 120 east, yeah, 120 east, and yeah, that's the longitudes and that's the latitudes. And again, that can be anything. You can look at your transect in the again helper function that called plot transect map, and we specify here that it's north polar projection, so you can have a look at this map. If you change it to the global projection, you see that how this transect looks on the global projection. In principle, if you have interactive notebook, if you turn on interactivity in your notebook, then you will be able to actually zoom to it. And what it shows with this red dots is the, yeah, it's basically the points of your transect. Okay, so then in order to create a transect, the minimum amount of data is just to provide the data itself, the mesh, and the coordinates of the points that form a transect. So again, it can be a zigzag or whatever. So that's your decision. Just point one by one the points that go next to each other, hopefully. This is the results of your plot. You can control different things, and the next few cells in the notebook will be just showing few capabilities that you can use to control it. So we can set up a maximum depth. So now it's 2000, before it was 1000. And you can label things. So now it's transect and degrees Celsius. You can provide some, okay, I have to execute this as well. You can provide some levels. You can provide the color map of your choice if you wish. And also you can plot 2 transects or 3 or 4, whatever, just next to each other, right? And for this, you just have to provide this three-dimensional PFESOM face, kind of in PFESOM thinking, but 2-dimensional in NumPy and usual Python thinking two-dimensional arrays, right? Basically, number of points and number of vertical levels, and you get two transects. Yeah, the very important thing is this face color thing that controls the color of this this area, which is your land. I'm not going to go into too much detail of like more controls. You can actually look at the internals of it, and this is again even lower level. So there is the way to actually extract the data that you that your transect consists of, right? So the data that was used to plot these things, and just do with them whatever you want. But right now I'm just showing the plotting stuff. Okay, there is a question here. Can we also compute transport through the sections? No, not yet. Not with pyfesom right now, but maybe Claudia, you missed it in the beginning. I mentioned that Dima Sidarenko actually provided the notebook in pyfesom that allows you to compute the transport on the original mesh. I still have to look at it to make it maybe a little bit more user friendly, but in principle, it is already, this functionality is already available. So you can do this, but not as easy as just plotting, just providing some, just using some function. So you have to do some extra work for it. And there is a paper actually in GMD submitted, and it's online, so you can have a look how it's done from the theoretical point of view, let's say. Okay. Another thing that is interesting, also related to Claudia's question, is UV transects. So again, without going too much into details, I just show you how it's done. And again, have to remind you that you don't have to use it to calculate the transport or anything like that. So it's just to have a look if you have this current, let's say, there or not, or if it's strong enough, let's say. But if you don't try to do any computations of this. And again, the reason is that we just get the data right now, and these data are now on, let's have a look at them, on the centers of triangles, right? So this is, oh, I mean, it's not clear, right? Shape. So this is 2 times larger than the number of nodes. So this data on triangles right now. And what I do first I interpolate from centers on triangles to the nodes. And then I work with this interpolated data to actually, well, I mean, this one is just creating the transect itself. So I work with this interpolated data, which actually took some time to interpolate, even for this smaller, small mesh, to create transect from UV data. What you get in return is rot U and rot V. Why it's rot? It's rotated. It's coming from the word rotated, and the reason is that the data that you get in PFlots from the PFlots directly are actually on the like rotated in a way that is in accordance to the rotation of the grid, internal rotation of the grid. The thing that I mentioned in the beginning that allows you to avoid a singularity in the North Pole, right? So the data that you get from PFlots, you cannot, they are not in geographical coordinates, this U and V component. So this they are rotated. So in order to plot them, you have to first unrotate them, right? So that's what this function do. It unrotates, like unrotates the U and V, and there is a function in pyfesom that is very old Python function, still from pyfesom2 that actually do this rotation. But anyway, so we first have to rotate them back and then interpolate them to this transect that we did. So to make this thing short, is in terms of computation of transport and so on is totally unprecise thing. There is no conservation of anything. But in terms of looking at the things, is good enough. So there is no problem to, if you see that there is a good strong current that is located between some depths, then you on original data you will see this strong good current located between these depths, right? So there will be no miracles in your, if you look at this data in the original data. So it's fine to look at the interpolated data, but no conservation. The numbers that you will get will be totally, well, not totally off, but pretty wrong if you start to compute transport. So please don't do this. Do this on the original mesh. Okay, and then when you get this rot U, rot V, you actually have to provide it to the plot transect. But again, here's a little peculiarity that you have to, instead of like this thing can be whatever because it's not used at all. What is used now is transect data. So in plot transect, there is a possibility to directly provide the transect data, distances, and nodes. This is also pretty useful, even if you don't plot the rotation like U and V. It's pretty useful if you work with large meshes. So just compute the thing once, and then provide the transect data, distances, and nodes. This is the things that you need to plot the transect, and you can then tune your visualization, let's say, without the plot transect actually recomputing your transect every time. Okay, and this is just showing that there is some currents here. One thing that is also probably useful for many of you is this my angle thingy. I don't know why I call it my angle, but whatever. Sometimes you want to do another rotation that makes your currents actually parallel to the slope. Well, I mean, I hope you understand what I mean, right? So if you make a transect perpendicular to the slope, you want to see that the currents, how the currents looks like, not in the geographical, let's say, coordinates, but how they looks like along the slope, so perpendicular to your transect. So and this you can control with this my angle thing. But for details, you have to look at the code, unfortunately. Okay, and this is, okay, we are fine on time. This is the last thing that I want to show you. It's something called diagnostics. The idea here is that it's a sort of high-level functions that I try to create in order to repeat the OMIP 2 exercises. It's sort of not even halfway through, but I mean, I think I already have an idea how I want them to look like. And just demonstrate the things that are available right now, and I think they are working fine. So here I just, again, just import the pyfesom and load the mesh just to repeat it. And here I'm trying to calculate the CI's, so-called CI's integral. In this case, I would like to calculate the ice area and ice extent over the data that I have in this path. So first, I have to get the right variable, which is aice, and this aice variable looks like this. So for this diagnostics, usually a preferable way, of course, is to use X-arrays, but they will work with both X-arrays and usual NumPy arrays. So you shouldn't worry about the X-arrays too much. So here I say compute how array is just better to put the none here. So the result will be the same, and then compute false so that you have the data, so there is no aggregation on them, right? And then you can compute ice area and ice extent. And the data are for 1948 to 1960, right? And the ice area is saved in our case on the monthly basis. So what you get back from the function ice area that you provide with this data and the mesh is the ice like area calculated for each time step. Since it's a X array, you can just make plot very easily, and you will have the plot of ice area. Same thing you can have here. And for more advanced features of what you can do with these things, you have to look at the X array. But the idea is that you like using very simple function call actually gets the relatively simple as well diagnostic, but yeah, there are some optimizations inside that hopefully make them a little bit fast. Okay, the question from the chat. Yeah.
So this is a global ice area. So it's not. Can you separate into northern hemisphere and southern hemisphere?
By default, like of course, it's a northern hemisphere. There is no like there is no sense in the global ice area, right, at all. So by default is northern hemisphere. I just make some sane defaults that are kind of can be applied without me thinking or any other person thinking about additional attributes. So that's most of the time. Maybe I'm wrong, but most of the time people you interested in, or like I don't know, 60% of the time people you interested in the northern hemisphere. So you can specify N or S here. Another thing that you can specify is this attributes, and the reason is that well, maybe it's also important to mention that the name of the variable that you get out of it is actually consistent with so it's basically a CMIP6 CMOR name. And you can specify some additional attributes that allow you maybe to save the data afterwards with some, yeah, so here you can specify additional attributes. So it will be global attributes for your netcdf file if you want to save a netcdf file. And to save a netcdf file in Xarray is just as simple as to netcdf, right? And then you provide the name for your file, and you get you get your data exported. I mean, this is again functionality of Xarrays, and that's why I find them very useful to work with. But that's not related to pyfesom. Okay, there was. Can I request AMOC as a diagnostic if that isn't already there? It's not there, but it's actually in. It's not AMOC, it's just MOC. The MOC can be computed very easily and will be added because it's just the matter of taking it from the current PFplots script that comes directly with pyfesom2. But AMOC is a little bit more complicated, but Dima already have the scripts to calculate AMOC, so if he will be nice enough to share the scripts with me, should be easy to do as well. But of course, AMOC is something that, yeah, is something that is very basic. And I know that, Paul, that you had some experience, but this is, I think, only related to the AMOC in pyfesom1. So we can chat about this later on. Okay, Huffmiller diagram. So basically what it does, okay, we have still some time. What the Huffmiller diagram does, let's first just load some data. It will calculate the mean the mean vertical profile over the whole ocean. So in the future, I will do it the way that you can actually separate it to different basins, and you can send the requests of your preferred basins in the issues. The idea is to use shape files for that. But right now, we just use the whole globe because this is what the whole world, because this is what the OMIP guys were interested in. And what you get back is again an array with 12 time points, because we have 12 years here, and 47 levels, right? So for each year, you have a mean vertical profile of your temperature in this case. You can plot it with Xarray, but it's not like super nice thing to do. So I would have to add some Huffmiller plot capabilities will actually expand a little bit the way how the data returned here, so that X-array actually can plot the vertical coordinate properly. But that's something again to work on. But the good thing is that you get the data. So the most important thing here, so for each year you can have a vertical profile and just combine them into the Hofmüller diagram. Hofmüller data is called. And the last thing, yes, the last thing is the volume weighted means. So here you can calculate the mean over some range of the depths. In this case, again, we use temperature because in this data we have temperature right now, and we specify that we want to calculate the mean temperature between 0 and 500. It will notify you that not 500 is used, but the closest level to 500, and then you can plot it. And this is your your temperature in the upper 500 meters from the simulation, and the years are here. And again, this is just the X-array object that you can use as an X-array object, and this is why we have this plot thing, right? Forget. The consequence of this is that you, what you have for free here is that you can actually calculate some temperature and some particular depth. In this case, it will be 590, and you just plot it. So this is the temperature at the depth of 500 for you. Yeah, so this functionality is going to be expanded. I hope to cover the whole, or most of the CMIP, not CMIP, but OMIP 2 functions. But right now, this is a limited set. But well, I think it's already can be useful for the others. I'm not gonna go to this low-level function thingy. It was done for some other presentation, let's say. You can have a look by yourself how to maybe calculate this area weighted things, or weighted area mean, and so on and so forth. But again, the code most of the time is really basic. So if you have a look at the implementations in the pyfesom, you should be able to grasp it, because there is nothing that is super complicated in there. And I hope to make it's even more readable, because some large-scale refactoring is needed, since we are not really following all the Python standards, and code sometimes is a little bit ugly to look at, but I hope it's understandable. Yeah, that's it. So if you have more questions, I will be happy to answer them now. If you have further questions, please do the issue and pyfesom repository. Are there any questions? I think I'll stop recording for now.